If one were to rank the elementary subjects of mathematics in order of complexity, one wouldn't imagine that the very concept of zero would actually proceed from arithmetic, negatives, percentages and ratios, geometry, trigonometry, musical relationships, local astronomy, and polynomial algebra. Yet the historical record proves that it did. And, in fact, in ancient historiography, a civilization's knowledge of the number zero, its applications and properties are, somewhat surprisingly, often used as a metric of advancement or sophistication, at least in the areas of science and mathematics. In the words of historian and mathematician Tobias Dantzig, quote, "The discovery of zero is one of the greatest single accomplishments of the human race," end quote. While a trivial concept to fully fledged modern adult minds, quote, "Zero is singled out by both educators and cognitive scientists because of its extraordinary properties. These properties make explicit computations involving zero more difficult for children to learn. They also make accounts of mental representations of it more intricate than those of 1, 2, and 3, its neighbors on the natural number line," end quote. In fact, as we'll learn later, simple computations with zero, particularly those related to division by zero, eluded zero's very inventor or discoverer, an error that remained uncorrected for even hundreds of years following the first instances of zero in writing. So, why the holdup? What belabored the discovery of zero for so long? Despite using, as do Arabic numerals, but unlike Roman numerals, a positional numbering system, albeit in sexagesimal or base 60, where the weight of a particular number is determined by its place value, the Babylonians did not have a figure for the number zero, instead using the equivalent of a space consisting of two angled wedges if a zero were to occur immediately within a number, but not otherwise. Furthermore, the Babylonians couldn't, or didn't, add or subtract with zero. In fact, it might even be disingenuous to understand the Babylonian placeholder symbol as being equivalent to or preceding zero at all. This, alongside a variety of other factors, renders Babylonian mathematics notoriously inscrutable. For example, the decimal symbol is also used within units, functioning as both a modern decimal point and something akin to a comma, e.g. 5280 and 5.28 would be indistinguishable, and therefore the value of particular numbers would have to be verbally indicated by a teacher or peer rather than being obvious given reading alone. According to McGill University researchers Dirk Schlimm and Catherine Skosnik, quote, "This does not appear to have been overly problematic for the Babylonians. Possibly this is because in a sexagesimal system, the difference between each place value column is quite large. After all, we sometimes identify numbers based on context even today. If a colleague said her house cost $450, it would probably be clear that she meant $450,000. But if she said that the sandwich she ordered for lunch cost $4.50, we would likely understand her to mean $4.50, end quote. This emphasis on and awareness of empty space actually engendered the development of a kind of figureless algebra where variables would consist of tangible examples and word problems. One problem reads, quote, "I've added 7 times the side of my square and 11 times its surface. The result is 6.15, or 6,150. Write down 7 and 11. Or alternatively, 11x squared plus 7x equals either 6.15 or 6,150. As you could probably tell, this 2,600-year-old assignment is posing a pretty simple quadratic equation, though the Babylonians would consider this problem as possessing only a single solution. In the Near East, the number 0 wasn't represented by a unique character until the Seleucids, one of the resulting dynasties of Alexander's conquest. However, 0's limited range of uses remained the same. In the first few centuries AD, Sanskrit mathematicians, who also used, at least amongst astronomical circles, a place value system, were the first in the Old World to employ a non-placeholder iteration of 0. A sophisticated knowledge of mathematics in this era, that of the Gupta Empire, was engendered by its broad relevance to both the specialized education required for members of guilds and the more theoretical body of knowledge provided by Brahmanical and Buddhist institutions. The weakness, at least relative to the Maurya Empire, of state control by the Guptas increased caste mobility and eased social order, and the relationship between caste and occupation became less stringent, perhaps democratizing mathematics. Brahmagupta, an Indian mathematician living in the 7th century, is frequently credited as the creator of 0, and as well one of the earliest authorities on negative numbers. However, Brahmagupta's understanding of his own number broke down when considering division, erroneously believing that not only is 0 divided by itself also 0, but that likewise any integer divided by 0 resulted in 0. His error wasn't corrected until the polymath Bhaskara, operating in the 12th century, realized that division by zero resulted in an infinite quantity. Another societal contributor to India's innovation of zero was a major difference in perspective in regard to what zero even is. The standard misconception in Europe, at least prior to the 1400s, and elsewhere purported zero as literally nothing. However, the Hindu phrase for zero, sunya, meant something like blank rather than true nothingness, perhaps a concept which one could more easily imagine performing operations on. That term, sunya, evolved into the Arabic equivalent Seife, or vacant, before finally becoming the Italian zero. However, even prior to Brahmagupta, ancient peoples in the Western Hemisphere were pioneering zero, its first recorded instance in Mesoamerica being a Maya carving from the 4th century AD, while monuments from even before Christ bear calendars contingent upon the assumption of zero, suggesting but not confirming an even earlier use. The Maya conception of zero had esoteric connotations, its character possessing a diametric literary use associated with mythical locations. The Maya and Mesoamerica in general attributed special significance to dating. For example, the mixed texts were often named after their date of birth, and calendars in specific, possessing 3 at any given time, including a standard 365-day secular calendar, a Venusian, as in congruous with the orbit of Venus, sacred calendar, and the famous long count, which measured the time elapsed since the supposed creation of the universe, beginning with, strangely, day zero, as in beginning prior to the elapse of a single day. One of the earliest inscriptions of a long count calendar date, as aforementioned, is dated to 32 BC, suggesting knowledge of zero as the predecessor to 1 as far back as the 1st century BC, assuming the system of dating remained consistent. Despite Arabic numerals arriving in Europe rather early, first being embraced by the scientifically minded Pope Sylvester II in the 10th century, the number zero was rejected by the Vatican and Europe at large, even into the early Renaissance. In fact, the earliest iterations of the Hindu-Arabic numeral system to reach Europe via Byzantium didn't include zero to begin with, although common in Byzantium from the 12th century onward and preferred by Sylvester, as aforementioned. Hindu-Arabic numerals didn't phase out their Roman counterparts until the 15th century. A second wave of Hindu-Arabic numeral awareness, this time including zero, occurred in the 13th century after Fibonacci popularized the system in his arithmetical work Libra Baci. However, all Arabic numerals, including zero, were banned in Florence in 1299 under the pretense they promulgated fraud. For example, an instance of zero could easily be manipulated to become a 9 or a 6, yet the benefits of the place value system were obvious, and merchants simply divided their papers between official documents, on which they'd write with Roman numerals, and personal documents, where they'd perform necessary, intricate calculations with the Hindu-Arabic. So, the widespread use of Hindu-Arabic numerals marched on, its legality notwithstanding. And the invention of the Cartesian coordinate plane in the 17th century further cemented zero as the average of 1 and -1 in the European vocabulary. However, as an Aristotelian philosopher, René Descartes was deeply unsettled by zero and the concept of nothingness, even denying the existence of vacuums, a question which would, of course, come to be settled by the experiments of Torricelli soon after. By successfully creating a vacuum in his mercury barometer experiment, Torricelli, alongside Blaise Pascal, the creator of probability theory, confirmed not only the existence of vacuums, but likewise the existence of atmospheric pressure, which contrasted with the Aristotelian assertion that air was an ever-present, weightless, even massless substance. While Descartes was concerned about nothingness and its apparent threat to the Aristotelian and Neoplatonic foundation of his faith, Pascal was ecstatic about the possibilities of zero and, furthermore, infinity in service of Christendom. You may notice that Pascal's famous wager is actually an expected value chart consisting of only zeros, true death states, and positive/negative infinities, afterlife states. For those unfamiliar, expected value is a measure in probability theory denoting the sum of one or more values multiplied by their probability of occurring, which corresponds to the profitability of a game of chance, provided enough time. For the sake of example, if you have a 1 in 100 chance of winning a raffle, the price of a ticket being $10 and the value of a prize being $100, the expected value of that investment would be 1 in 100 multiplied by 100 subtracted from 10 plus 99 in 100 multiplied by -10 or -9, i.e. unprofitable. As aforesaid, the trick of Pascal's wager consists in the decided value of two afterlife outcomes. Both heaven and hell are considered infinities, total suffering and conversely total pleasure. Thus the total expected value of theism is also infinity, no matter how low the estimated probability of God's existence actually is. One might question the complexes which motivated our ancestors to expend doubtless amounts of mental bandwidth to skirt around concepts such as zero, negatives, and imaginary numbers for ostensibly common sense reasons, by and large relating to doubts regarding their ontological existence, less undeniably obvious than that of natural quantities, though that's still a continuing problem in the philosophy of mathematics. The correct lesson to derive from the history of zero is that very fact, the suffocating influence of common sense, and the unobvious practical value that incessant, even borderline dumb, inquiry possesses. At any given time, you should be asking yourself this: what's the obvious thing we're missing? There's a high premium on the answer.